This step is necessary to assure that the position of the jack is correct with relation to its distance under the roller. When the jack is in the correct position, it will allow for the most efficient transfer of energy to the roller and at the same time be an optimum position for fastest repetition. The position is correct if the plane of the top of the jack addresses the roller in such a way as to be a tangent to the roller, touching at the point that represents the most efficient place to transfer the energy. This is accomplished by aligning the edge of the jack nearest the hammer to the edge of the wooden core in the roller that is also nearest the hammer. Adjustment for this alignment is challenging even to the best of regulators, and accuracy depends to a great degree on the position of the eye during the adjustment. One should get the eye in the same plane as the back surface of the jack, then turn the regulating button that is on the jack itself until the correct position is reached. It is easier to see the top of the jack and its relation to the core wood of the roller if the repetition lever has been depressed slightly below the top edge of the jack. Once the adjustment is complete on the first unit, raise that hammer assembly until it stands by itself and proceed to the second adjustment. Continue until all have been checked and properly regulated. With all hammers standing, check to see that the jacks form a straight line. If any are found that do not conform, recheck by the method just described. Proper alignment with the roller takes precedence over a straight lineup of the jacks, so leave any jack out of a line with its neighbors if that jack is properly aligned with the roller. The body of the tool used must be made of material that is small enough to fit between the let-off regulating dowels easily. Many tools are too large and may damage the let-off regulation dowel alignment as they are forced into position. At least, they're too large to be used comfortably. To make sure the jack does not slip out of its position on a hard blow, restrain the hammer's rise by holding it in rest position and giving its key a firm blow. If the jack slips out, jack position is not far enough under the roller. One can compare the jack in the piano with the jack used to change a tire on your automobile. In the case of the automobile, it is easily seen that the jack should be positioned correctly. Any position that is not perpendicular to the surface of the road is dangerous and will not allow the jack to do its job. In the same way, for the jack in the piano to do its job properly, correct alignment to the roller is essential. The essence of control and creativity enjoyed by the pianist is, to a great degree, afforded by the jack transferring energy to the roller. If the jack is not properly positioned, the piano cannot function as it should. Give the piano and the pianist your best. The real secret of fast repetition is not how fast the jack gets out from under the roller, but how fast it can get back to its original position so that it is ready to lift the hammer again. When the height of the repetition lever is correctly adjusted to be just above the top of the surface of the jack, and the repetition spring tension is correct, the repetition lever will support the hammer assembly and the jack can return without obstruction. In this way, the speed of the repetition is not hindered. The top surface of the repetition lever should be only slightly higher than the top surface of the jack, in the range of 0.2 of a millimeter. This can be tested by feeling the relative position of the two surfaces with the tip of your finger. If the repetition lever is set too high above the top of the jack, the equivalent of lost motion is created, and the extra clearance doesn't help return the jack any faster. Raise a section of the hammers. The keys will push the whippings upwards, and the drop screw will stop the upward travel of the repetition lever. To check the relative height of the two surfaces, use either the regulating tool or your fingers and depress the whippings on both sides of the one being checked. This will allow unobstructed access to the area around the top of the jack when checking the relative heights of the two surfaces. Before you pass your finger across the two surfaces, slightly depress the whipping, just to the point that the repetition lever has been pushed away from the drop screw. Make the test with the repetition lever floating in this manner. Using this approach, the the weight of the key will not produce an erroneous reading as it might if the weight of the parts forcing the lever up against the drop screw depresses the lever a bit. Also, the pressure of the lever against your finger will be uniform on all the levers as you test them. The adjustment is made by turning the regulating screw found on the repetition lever, but before the adjustment is made, disengage the two felt surfaces before turning the screw. In this manner, the felt will not bunch up and the adjustment will remain stable. The usual test the technician applies to make sure the jack will return is made with the parts at rest. However, when the piano is actually being played, the jack returns to rest position before the hammer has fully dropped, while the action parts are close to the string and those action parts are still in motion. Even if the normal way for the jack return is during a time of action movement, it is essential that the jack return to its place of rest in all cases. Therefore, you should check the ability of the jack to return in cases where the parts are at rest and have no inertia to help the jack overcome an obstruction. One way to test the jack in the rest position is to grasp the tail and carefully move it up and down. The downward movement makes the top of the jack escape from the roller, and the upward motion of the jack tail makes the top of the jack return to its correct rest position. You should feel a slight stroking of the roller's buckskin as the jack is moved, but the jack should be able to return by the tension of the spring alone, unassisted by your fingers. Another test is to depress the key in such a manner as to put the hammer in check. Then, very carefully, release the pressure that holds the hammer in check, but do not let the key rise. You will notice that the hammer rises. Now slowly allow the key to rise and observe the movement of the jack. By the time the key has returned to rest position, the jack should be fully under the roller. If not, the probable reason is the repetition lever is too low in relation to the top of the jack. On the other hand, if the jack quickly snaps under the roller at some point, it is probable that the lever is too high compared to the top of the jack, and too much lost motion exists. Often the surfaces of the lever on each side of the jack are not the same distance from the top of the jack, creating two different measurements. This is unavoidable and caused by a slight tilt to the lever that was created during parts manufacture. In such a case, one of the measurements should be set at the correct height, and the other measurement will be more than that. If the other measurement was less, the jack would not be able to return to its position of rest. The only tool needed is the one that fits the repetition adjustment screw. The one large difference between a grand action and a vertical action is that the grand has a repetition lever. However, the lever loses its value in direct proportion to how poorly it is regulated. Remove all lost motion, but make sure the jack can return under any circumstance. Then the repetition lever can live up to its name. This step will set the measurement from the top of the hammer to the underside of the string. The hammer needs to be set at the maximum distance from the string that is practical, given the engineering design of that action and the amount of aftertouch required. The distance the hammer travels is a primary factor participating in creating the speed at impact with a given force depressing the key. Thus, it greatly influences the energy transfer and the control available to the pianist. The measurement should be obtained from the manufacturer, and in the case of Yamaha Grands, it's 48 millimeters. In case the hammer-to-string distance is not available in print, it can be deduced by knowledge of the engineering principles of action design. The use of a jig made to the specification is preferable to using a scale, for small deviations from the measurement are easier seen by using the jig. Depress the right pedal in order to remove the dampers from the area being tested. Then insert the tool between the strings and check the distance. When an adjustment is needed, turn the capstan in the appropriate direction. In this step, we are only setting samples, so you should set one hammer at each end of each section. If, after setting the height of the hammer to the specified measurement, the hammer shank is touching the hammer shank cushion, or if the key does not have enough aftertouch, the capstan should be raised to the point that either or both of the problems are solved. It's possible to create more aftertouch in a number of ways, but we will assume that the only variable for this situation is the hammer to string distance. If we are checking for aftertouch, key dip has to be correct. Since the depth of the black key has not been set yet, to set samples we must use only white keys at this point. Besides the measuring tool, a capstan wrench will be needed. If the piano has a very long section of hammers, it would be a good idea to set another sample, this one in the center of the long section. Use care with this adjustment. It has a great effect on the finished job. After completing this step, you should have set 2 hammers in each section, each at the proper distance from the string. In the next step, we'll adjust the hammers between the samples. In the previous step, the correct hammer to string distance was set on only 2 hammers in each section. This step is a continuation of that previous one, and information will be given that is helpful in matching the height of the remaining hammers with those samples. To accomplish this, all that is needed is a capstan wrench and some sort of guide to compare the hammers against. Pull the action partway out of the action cavity to a point where the hammers are directly under the upper front beam. The bottom of the beam is a straight line and provides a very good target to view against. In this position, the balance rail area of the key frame can be pivoted on the front edge of the key bed, thus bringing the hammers very close to the underside of the beam. Adjust the capstans as needed to raise or lower the remaining hammers using the beam as a guide. The tops of the hammers should match the height of the samples and form a straight, level line. To make sure the adjustment remains stable, it's a good idea to depress the keys forcefully, making the hammers strike against the underside of the upper front beam. This will compress the felt above the newly adjusted capstan and ensure stability. Recheck the hammer line again after this procedure. Keep in mind that uniform aftertouch can only be accomplished if each key, weapon, and action unit moves exactly the same amount. If one hammer is lower or higher than another, the aftertouch on that unit will be different. At the time the first piano appeared, it was really the principle of escapement that had been invented, not the piano. The remainder of the early piano was basically a harpsichord. This is not to take anything away from Cristofori, but to emphasize the importance of the escapement principle. At the heart of the escapement sequence is the adjustment of let-off. During a very slow depression of the key, the mechanics of escapement controls how close to the string the hammer will get before the jack escapes and the hammer drops after losing the support of the jack. Precise adjustment is necessary, for the closer to the string the hammer can get before let-off occurs, the more power and control is given to the pianist. On the other hand, this adjustment must not allow the hammer to move too close to the string, or the hammer may block or otherwise interfere with the string's vibration. Since the larger, longer strings of the bass area create larger patterns of vibration than do the smaller, shorter strings, it's obvious that the let-off distance has to be a bit greater on the longer strings. The measurements are correct when the hammer to string distance at the highest point on hammer number 88 is 1.5 millimeters and 3 millimeters on hammer number 1, and graduates smoothly in between. The adjustments are made by rotating the let-off dowel found just above the jack tail. It's difficult to actually measure let-off distances, but one way to approximate the correct measurement is to visualize the diameter of the string in question. The highest point to which the hammer rises should leave twice this distance between the top of the hammer and the underside of the string. The sizes of the strings become larger as one progresses down the scale. They change diameter every half dozen unisons or so. There's a direct relationship between the larger diameter of the strings that produce the tones of lower pitch and the measurement let-off needed on those larger strings. As the string's diameter becomes larger, the let-off distance should become greater. By using the distance of 2 imaginary string diameters as the measurement, It is possible to match the required distances of a graduated let-off almost exactly until one sets let-off on the wound bass strings. The let-off distance under wound strings must be measured by two thicknesses of the core wire only, without considering the diameter of the copper wrapping. The relationship between the top of the hammer and the underside of the string is difficult to see in the upper sections of the piano. The use of a mirror will help where vision is restricted by the capodiastro bar. The adjustment should be made in the piano, and the tool to use is called the let-off regulation tool. A very popular type of let-off regulation device is the let-off dowel, as seen here. In this case, the tool used is the same as the capstan wrench. Be sure the tool fits into the hole fully, for the size of some tools is larger than the diameter of the holes in the dowels, and if only the tip of the tool is inserted, damage could occur. Check the spacing of the let-off dowels at the same time, and carefully correct any that are not in line. This can be done by bending the post the dowel is fitted on, and should be done only if the correction is possible without injury to the dowel. Perhaps a summary and an important test should be mentioned at this point. First, let-off should be close to the string, but since the bass strings vibrate in larger patterns, let-off must be greater there. It should be 3 millimeters in the bass, graduating to 1.5 millimeters in the treble. Then, test the adjustment as you create a very soft sound by gently striking each key. No blocking or bubbling should occur, as might if the let-off is too close. That should take care of this procedure. Just remember, the let-off adjustment is something like focusing a camera. When it is exactly correct, the performance characteristics become much more precise, and the playability and control given the pianist dramatically improves. Step 22 deviates from the usual procedure of adjusting by means of physical measurement, and instead the depth of the black key is set by a sense of feel. The purpose in proceeding in this manner is to provide the pianist with a sense of touch that is not only correct and uniform, but also very comfortable. The goal is to set the black key depth to give the exact duplication of aftertouch feeling found on the adjoining white keys. If one has followed the steps leading up to this point, only the white keys have been regulated sufficiently by those earlier steps to make a test of aftertouch. To check black key depth for a sense of feel, all adjustments, including the adjustment for drop covered in the next step, need to be correct. This means that it may be necessary to check drop and make any remedial adjustments as you proceed with setting the black key depth. As a practical matter, step 22 and step 23 really need to be done simultaneously, but we have separated them to make each easier to understand. Remember, the goal we are pursuing is a feeling of uniform aftertouch on all keys. To proceed, place the index finger from both hands on the same white key and slowly push it downward about 1/2 of its travel until you feel a small bump, indicating that the jack tail has touched the let-off button. Your actions so far have just set the key up for the test and are not part of the actual test itself. The test to experience the aftertouch sensation is as follows. First, starting with the key partially depressed as just described, push the key all the way to the bottom of its stroke with a firm, definite movement with the approximate speed it would normally take to produce a mezzo-piano volume of sound. During the downward travel of the key, be aware of at least 3 items affecting the sense of touch in your fingertips. That is, the friction caused by the jack escaping from the roller, the distance your fingers travel in a downward motion, and the type of feeling at the bottom of the stroke, like firm, mushy, spongy, so forth. By using the white key as a standard, the difference in travel of the black key can be ascertained. While it is almost impossible to put the sensation into words that would mean the same thing to everyone, the feeling we are looking for should be a definite friction during escapement, but a very clean release, a depth of travel that is natural and comfortable, and a solid, firm end to the keystroke. If we have regulated correctly so far, the white keys will be a good standard to use. To correct any problems, change the amount of paper punchings at the front rail of the black key. Always check with 2 white keys just in case an error exists in the key dip of one of the white keys. If a difference in aftertouch is found between 2 white keys, recheck step 15. The only tools needed will be dictated by the manner in which you add or remove the punchings. Usually a set of tweezers is used, but it can be done with your fingers. Of course, you will need an assortment of paper front rail punchings. Remember, this step should be done in concert with the next. That is, in order to set the travel of the black keys correctly by the sensation of aftertouch, it is necessary that the drop adjustment also be correct. And ironically, at the same time, one of the tests for correct drop depends on the proper travel of the black key. A more accurate name for the drop screw would be stop screw, for its real function is to stop the upward rise of the repetition lever. Without the drop screw, the repetition lever would continue to lift the hammer into the string and it would block there. Probably the name drop came from the piano technician, for it visually describes the motion of the hammer after let off. In other words, the adjustment of the screw is to limit the upward travel of the repetition lever and not really for the amount that the hammer drops after let off. Be that as it may, the amount the hammers drop will be about 2 or 3 millimeters on most pianos, and in the case of Yamaha, the amount the hammer drops after the highest point of let off should be 2 millimeters. According to action design and to the artist's sense of touch, the repetition lever should touch the drop screw at the same time the jack tail touches the let-off button as the whippen is traveling upward. This will create one solid point of contact rather than 2, and will eliminate the spongy feel in between the 2 that is annoying to the musician. For making the correct judgment, one must understand the complete movement of the hammer. It can be said that with a slow depression of the key, the hammer makes 3 definite movements. The first is from its position at rest up to the highest point of let-off. The second is the period of drop itself, measured from the highest point of let-off to the lowest point the hammer falls. And the third is the small upward movement of the hammer that it rises after the low point of drop. If care is not taken, it is easy to join the last 2 movements and thus get a reading for drop that is less than it should be. The way to avoid this error is to restrict the free movement of the key by some means, like placing a finger below the key and pressing into the finger. In this way, you can control the downward motion of the key and stop its travel precisely when the drop has finished, but before the additional movement of the key causes the second rise to take place. The drop screw is only accessible when the action is out of the piano, so care must be used to check the adjustment in the piano after setting it. Drop can be adjusted without using another hammer for comparison, but it is easier with the other hammer there to look at. If a hammer that is already properly adjusted is held either at the high point of let-off or with the key all the way down so that the second rise has taken place, it can act as a comparison for checking the drop on the neighboring key. Finally, when the adjustments are all made, you should check the uniformity by placing the action back in the piano and press a group of keys all the way down. The resultant line of hammers in the piano should be a straight one. The tool needed would be the type of tool that fits the drop screw. Sometimes it's a small screwdriver, but on Yamaha pianos, it is the same tool used for the jack position and the repetition lever height adjustment. Drop adjustment is essential for proper touch inasmuch as the differences are easily felt by the pianist. Differences in actual amount of hammer drop are not perceived. Instead, the feel of the repetition lever touching the drop screw on its way upward is the important point, especially when playing pianissimo passages. Another item is the feeling of touching a solid shelf or platform that's created when the adjustments of let-off and drop are precisely regulated. When the key is depressed about 50%, the pianist should feel this platform. It's especially important for control during soft passages, for in order to play a pianissimo volume, the pianist may not use the full travel of the key. In reality, this step is just a check, not a separate adjustment as the other steps have been. This is a place to make sure the piano will play properly, uniformly, and comfortably. It is the assurance that not only the manufacturer specifications be fulfilled, but also the pianist will enjoy performing on the instrument. The total subject of aftertouch would fill a volume and is covered as a separate subject on another tape in this series, so some understanding of this point will have to be assumed. In general, we can say that when regulation is correct, all the adjustments will be in the proper place to satisfy the specifications and the pianist. There is a visual indication of aftertouch. It is the slight hammer rise that follows drop and is proof of escapement. The amount of rise is an indication of the amount of aftertouch. A small rise means a small amount, and a large rise indicates a larger amount. If pressed for a definition, we could say that aftertouch is the amount of key movement, and therefore the amount of complete action movement, that follows the precise point where the jack just escapes from the roller. However, the term aftertouch implies feelings rather than a measurable specification. Feelings are individual and difficult to express with words. But since words and measurements are the main tools technicians have to work with, let's try to see the picture or get the feeling using those tools. At the end of the keystroke, after the tone has sounded and the hammer is in check, the jack will be in some final position. This position is a very important consideration to aftertouch. Movement of the jack must be enough to allow the top of the jack to escape from the roller, but after its escapement, the jack must not move so far as to block against the cushion that is found in the front of the window of the repetition lever. It's difficult to arbitrarily assign a definite amount of aftertouch, for many points must be considered. Pianists require different amounts, different piano designs dictate different amounts, action wear will change the ideal. In any case, however, the limits of aftertouch are set by the restrictions placed upon the jack's position when the key is fully depressed. On the minimum side, the jack will stop at a point that is near the roller, but it has to completely escape from the roller even on the lightest blow. And the maximum amount of aftertouch will occur if the jack ends up the greatest distance from the roller, but there is a limit. It should not block against the cushion when the key is struck very forcefully. When the amount of aftertouch, or in our terms, the final position of the jack, is not correct, 3 adjustments should be considered. Those adjustments are key height, key travel, and hammer to string distance. If the aftertouch, therefore the jack position, requires change, usually the reason is some small mistake of adjustment in one or more of the steps that lead to that point, rather than an incorrect set of specifications or a poorly designed piano. This means that before changing one or more of the adjustments from a correct specification, you should first check the prior steps to see if a mistake has been made. If none are found, then you should improve the action by one or more of the 3 adjustments of key height, key travel, or hammer to string distance. The adjustment used and the amount of change is determined by the situation. Even though aftertouch is a sensation, a physical feeling, the distance the jack can move from its point of escapement from the roller to the block in the repetition lever's window can be useful as a set of limits to place the jack within in order to produce the proper aftertouch. Step 25 is the first of 3 steps having to do with the proper regulation of the back check function. The purpose for the full set of steps is to first stop the movement of the hammer after it has struck the string, to allow for very quick release of the hammer once the key is released, and to stop the hammer at the highest point that is practical. The purpose for this first step that is the step of back check alignment, is to position the back check wire and the rotation of the back check on the wire so that the hammer tail will contact the back check squarely. From the back of the action, lift each key and check the vertical alignment of the sides of the back check with each other and the vertical alignment of the back checks to the hammer tail when in check. To correct either problem requires the use of wire bending pliers. In most cases, to correct a problem that requires bending a wire necessitates bending the wire twice, once at the bottom to lean the wire in the direction needed, then again at the top to return the top section to the original plumb or straight up and down position. Next, check to be sure that the hammer tail touches the back check with the same pressure at all points of contact. If this needs adjustment, it's because the back check has rotated on the back check wire. To correct, just twist the back check in the desired direction. A note of caution: it's better to turn the back check with a tool rather than with your fingers. The tool is simply a piece of wood fashioned in the manner of an open-end wrench, with the opening between the jaws the same as the width of the back check. If the part is rotated by the use of your fingers, damage to the buckskin and to the glue joint holding the buckskin could occur. Continue the process until all back checks are correct. At the same time, check for evenness of spacing between the back checks. If the hammers are spaced properly, the back checks will be equally spaced as well. The tools needed are the wire bending pliers and a tool for rotating the back check. Without this step of alignment, it is impossible to accomplish good hammer height catching. And without proper hammer catching, performance will suffer. This step has to do with catching or stopping the hammer and more. Speed of repetition depends on the quickness of release from the back check. One of the most important functions performed by the back check is to release the hammer quickly after it has been caught. One can imagine that a very sticky surface like flypaper could stop the hammer, but the tenacity of the sticky substance would certainly slow down the ability of the action to repeat. The angle of the back check, coupled with the design of the back check and the materials used, solves both problems of quick stop and quick release. Usually, there is no need to do anything at this point if the piano was regulated properly when it was constructed. If the angle has been set correctly once, the angle will not change during the life of the action. The real value of this step comes into play when the back checks need to be replaced, and one must set a new angle at that time. Most all of the bending that is done by the technician is for height of catching, and that type of bending will not change the angle of the back check on the wire. For the bending controlling the height of catching occurs at the bottom of the wire, and the angle of the back check is controlled by the bend at the top of the wire, just under the lower edge of the back check. To understand the angle concerned and its function, take a look at the side view of the action. Focus on the area of the back check and hammer tail when the hammer is in check. The angle the back check addresses the hammer tail is the one in question. To correct a problem, the wire is held securely just below the back check with the wire bending tool, which, by the way, is actually misnamed, for it doesn't bend the wire, it holds it stationary like a vise would. The bending is accomplished by moving the back check with the fingers. If the top of the back check is moved away from the hammer, the angle of the back check will become greater. As the back check angle is increased, at some point the tip of the tail of the jack would bounce away from the back check and there would be no checking. On the other hand, if the top of the wire is held securely and the top of the back check bent toward the hammer, at some point there would not be enough angle exposed to the hammer tail and it would not check well. And if it checked at all, it would check at different heights depending upon the force of the blow. The angle is correct if the hammer catches well even on a light blow, and once it is in check, the finger meets with increased resistance as the hammer is forced further into the back check. To adjust for correct angle, set one back check by the parameters just mentioned, then line up the remaining back checks to that angle. This can be done by visually inspecting the alignment of the wood surfaces of the back checks. Remember, when this bend is made, it has to be made at the top of the wire by using the correct tool. Uniform hammer height when in check is a prerequisite for this step. If catching height is not correct, perform step 27 first, then return to step 26. Factors that influence repetition are the back check angle, the amount of cushion in the back check, the strength of the wire, and the surface of the hammer tail in the contact area.
A couple of words are in order concerning the surface of the tail of the hammer in the area where it contacts the back check. The major reason the back check principle works is not by the friction between the two surfaces, but instead because the surfaces are each traveling on separate arcs that intersect, and after the intersection, one arc moves inside the other circumference.
This means that after the two surfaces have made initial contact, they will press against each other with greater force as the key moves the back check upward. In other words, the function of stopping the hammer is created by the back check pushing against the hammer tail, not by the simple friction created by the roughness of the two surfaces. Therefore, the surface of the hammer tail should not be any rougher than necessary, for extra roughness will not improve the back checking, but will cause unnecessary wear of the buckskin on the back check. Usually, all that is necessary is to stroke the hammer tail a few times horizontally across the surface with a file, or perhaps with the teeth of a small piece of hacksaw blade. The tools necessary are the wire bending pliers, the wire bending tool, a file, and a piece of hacksaw blade. And I'd like to repeat this point. Remember that the manner in which the catching function works is based upon pressure created by arcs of two intersecting circles, not by simple friction between two surfaces. The tail of the hammer has to be rough enough to cause some friction, but too much roughness is detrimental. With the last two steps, we have prepared the back checks to properly catch the hammer. So let's move on to setting the height of the hammers when caught by the back checks. The purpose of step 27 is to stop the hammer after it has rebounded a short distance from the string. 15 millimeters is the measurement called for by Yamaha, and most of the other manufacturers use approximately the same measurement. It would appear that the hammer should be caught as close to the string as possible, but experience proves that if the hammer is caught much higher than 15 millimeters, it will create a problem of touch that the pianist can feel when playing fortissimo. With the action in the piano, usually you can find a hammer that checks at the proper distance from the string. If not, experiment by bending the back check until one is correct. Remove the action and compare the adjoining hammer when in check with this hammer when it is in check. If they are not at the same level, grasp the back check with your fingers and bend it either toward or away from you until the hammer catches at the height that matches this correct sample. Bending the back check wire by this method will cause the wire to bend only at the bottom where it goes into the key, never at the top where it would change the back check angle. Continue this procedure until all hammers catch in a straight line at the height of the sample. As a final check for accuracy with the action in the piano, play a number of white keys with one hand and the black keys they enclose with the other hand. The tops of the hammers held in check should form a level, straight line. If the hammer is caught too close to the string, the back check will be too close to the hammer tail, and on a very hard blow will rub against the hammer tail as the hammer ascends toward the string. This problem may not be noticeable during the time the pianist is performing at a volume less than fortissimo, but can be avoided altogether. Just apply pressure on both the key and the hammer simultaneously while working both of them up and down. There should be enough clearance between the two that they will not contact each other during this test. No tools are needed, save the educated hand and the experienced eye. Correct back check height is essential for fastest repetition, and in addition, irregularities of catching can be felt by the pianist, especially upon the release in pianissimo passages, as the repetition spring creates different distances of hammer movement, returning the repetition lever to the drop screw. With the proper tension on the repetition spring, the repetition lever can correctly support the weight of the hammer assembly and allow the jack to return underneath to its place of rest. Of course, the reason for the existence of the repetition spring is to speed up repetition, and this being the case, simple logic would require that the spring must be as strong as is acceptable, never too weak. Incidentally, many, if not most actions, have one continuous spring for both the repetition lever and the jack. Therefore, the proper tension on the jack spring is automatically regulated at the time the repetition spring tension is adjusted. If one is to regulate an action that has a screw adjustment for changing the spring tension, the manner of changing the tension is very obvious. However, many action designs, including Yamaha, use a spring that does not have a screw to change the tension, and any change must be made by manipulating the spring wire itself. In this case, one end of the spring is placed in a receptacle in the jack, from which the spring wire goes to a coil that is centered in the repetition lever support post. The other end of the spring goes into the underside of the repetition lever itself. This double-ended or butterfly spring might remind one of a safety pin. In the case of the safety pin, to strengthen the spring, one would grasp the two ends that come from the coil, one with either hand, and pull the two ends apart. This would enlarge the coil where the spring tension resides. To weaken the spring, one would push the two ends together. So it is with the repetition spring. To strengthen, one would unhook the spring and lift upward on the end so that the coil is strengthened. To weaken the spring, one would push the top wire downward. For a very small adjustment, you can place the tool under the belly of the spring and lift upward as you stroke the tool back and forth, rubbing the belly of the spring. Probably the most intricate part of this step is performing the test to find the strength of the spring. It is done in this manner. First, it is possible to check the speed of the rise with the action in the piano, and perhaps this is a good place to start. However, any adjustment that is to be made requires that the action be out of the piano, so I will describe the procedure with the action out of the piano. Push the key down with enough force to cause the hammer to rise and then fall into back check. Be careful, for if you press too rapidly, the hammer will rise too far and may break at the flange area. The hammer needs to be checking at the proper height. Slowly release the pressure on the key, but do not release the key entirely. Observe the action the hammer takes as the tail is released from the back check. It should rise to a point where the repetition lever touches the drop screw, traveling all the way with a definite movement. The speed of the rise of the hammer is different throughout the keyboard, with the lowest bass hammers rising slowly but definitely, the mid-range hammers rising faster but without much of a bounce at the top, and the treble hammers rising fairly rapidly with a slight bounce at the top. The key to judging the speed of the hammer rise is twofold. One is the speed of rise as seen with the eye, as just described. The other way is in a sense of feeling, in the finger that is on the depressed key. When the repetition lever touches the drop screw, a bump will be felt. The amount of bump is the point of judgment. If the spring causes the hammer to rise so fast that the contact is strong enough to send a shock to the finger that is noticeable, one that the pianist finds annoying, then the repetition spring is too strong. However, the amount of shock that one pianist finds annoying may be totally acceptable to another musician, so judgment must be used. The final check should be made in the piano. A couple of notes of caution. The end of the spring and the slot it works in should be clean and well lubricated. In many cases, the original lubricant has absorbed dust and the friction has increased. It may appear that the spring is weak when in fact the spring tension may be all right, but the friction in the spring slot is too great. Be careful that the spring has been inserted correctly into the spring slot. If accidentally left on the shoulder, it will work its way off and become disengaged. If this happens, the key will not function at all. If the springs are weak, hammer height may change after completing this step. Only the regulation spring tool is needed, but it should be constructed correctly. Observation of the sample Yamaha tool will explain the construction needed. Erard's invention of the repetition lever and the repetition lever spring at the beginning of the 19th century made possible the grand action as we know it today. Without proper repetition spring adjustment, the grand action loses one of its finest points of performance. Perhaps this small strip would better be called a shipment rail, for its only value is to restrain the keys during transportation. It is positioned just over but not touching the keyboard and is found directly behind the black keys. In this position, it is ready to keep the keys stationary during the time the piano is on its side while being transported from one point to another. It is usually fastened to the key frame with screws at each end and is supported in the center by 2 or more posts. These posts are threaded rods, and in addition to being firmly embedded into the key frame, they are supplied with 2 nuts each. The rail is suspended between the 2 nuts, and its height can be changed by adjusting them. The standard that should be used is that the top of the black keys, which are closer to the rail than the white keys, should be about 1 millimeter below the rail. Or to state it more correctly, the rail should be about 1 millimeter above the highest keys. Adjust the height in the center area by turning the nuts in the correct manner. Remember that the final step should be to turn the top nut down securely on the rail so that the adjustment will not change. If they become loose, the nuts might vibrate, causing noise and a possible change in the height of the rail. If change is required at either end, proper blocking under the key stop rail is required. If the rail is a bit warped or the adjustment a bit low, the rail will press the key down slightly and cause the hammer line to rise. Your final check should include attention to this possibility. A screwdriver of normal size is needed for the 2 screws, and a small screwdriver is usually needed to fit in the slot in the nut of the center fitting. As you can see, this rail is very simple to adjust, so we will not spend much time talking about it. In this step, we'll make sure that the damper system works freely, but without undue vibration of the head of the damper. Since all centers were inspected and corrected in Step 7, the only remaining areas to check would be the fitting of the damper guide bushing around the damper wire and the bends in the damper wire. The hole in the damper guide should be just larger than the diameter of the wire. In current production at Yamaha, the wire is 1.8 millimeters in diameter, and the hole is sized at 2 millimeters. If the hole is too large, the damper will not be stable, and the vibration of the damper head, as well as the speed of damping, will be affected. Of the 2 bends in the wire that form the dog leg, the lower one controls matching the bottom of the wire with a hole in the flange, and the upper bend controls the angle the wire has in relationship to the guide rail. If either bend is incorrect, friction will occur at the guide rail, which will result in loss of good damping. The first test should be to remove the action and lift several damper levers with your hand. Check for a sluggish feeling as the dampers descend. If the dampers are completely free, the levers will stay on top of your fingers, and the feeling will be as though the levers were dead weight, exerting the same pressure on your fingers whether or not you're moving them. If there's friction, the weight of the dampers will appear to become less as they descend. If correction is indicated, it will either be that the bushing is too tight around the wire, or the wire is pressing against one side of the bushing. The latter is caused by incorrect bends in the wire. To correct for a tight bushing, first try lubrication. Yamaha recommends pure silicone oil thinned with naphtha. But if the fitting of the bushing around the wire is too tight to be solved by lubrication, enlarge the size of the hole by inserting the umbrella rib tool. This tool can also be used with heat if necessary. To correct an improperly bent wire, the process is done in 2 steps. First, loosen the screw in the damper wire flange and move the lever up and down, allowing the wire flange to slide up and down on the wire. If you encounter friction during movement, correct the bottom bend in the wire by the use of wire bending pliers until the wire flange slides freely up and down on the wire. Retighten the screw with the wire in correct position for damper lift. Next, raise 3 levers simultaneously with the one in question in the center. Observe the damper heads. If the center damper head moves either to the left or right, the top bend is the problem. Carefully bend the top bend until the center damper head travels correctly, which means without movement either to the bass or treble, compared to the other 2 damper heads. Since dampers work by gravity, the path of least friction for the damper parts to travel would be directly towards the center of the earth. Usually the strings of the grand piano are parallel to the floor. Thus they are strung at right angles to a line pointing to the center of the earth. The angles between the damper head and the damper wire reflect this right angle relationship. A damper placed on a simple jig will indicate whether or not the wire leaves the damper head at 90 degrees. Bend the wire at the damper head to correct this until it matches the line drawn on the jig. When the jig is not available, the same test can be made by placing the damper on the upper front beam. Placing the damper head in a different position will show whether or not the wire is parallel with the side of the damper head, and thus it will show if the top part of the wire will slip through the damper guide rail correctly, and if the end of the wire will slip into the hole in the damper wire flange without friction. Bend the wire at the damper head in the proper direction until the two parts of the wire are parallel with the jig. These tests will assure that the damper wire will slip through the damper guide rail bushing correctly. The tools needed are a small screwdriver, wire bending pliers, and material for lubrication. Dampers serve two main functions. One is to stop the string from sounding, and the other is to allow the strings that should be sounding to do so. In most grand pianos, there are three ways of disengaging the dampers from the strings. These ways include the use of the right pedal, which removes all of the dampers from the strings, the middle pedal, called the sostenuto pedal, which sustains any number of notes that are already sounding before the pedal is pressed, and the subject of this step, lifting the damper by the use of the key. In the early stages of piano development, the only way the musician could raise the dampers was by the use of the keys. This dictated that any note to be sustained was taken care of by simply holding the key down. As music progressed and the piano improved, it became an advantage to lift the dampers from all of the strings at one time. A pedal to be manipulated by a foot was devised for this advancement. This pedal also made it possible for the sympathetic reaction of one string on another to build volume and tone color. And finally, when it was found that one tone or a group of tones needed to be sustained without the entire damper assembly being lifted, and the pianist's hands were otherwise occupied, the sostenuto or middle pedal was created. It's our concern to discuss the first of these choices, the lift of the damper by the key. There are special cases that allow for slight deviation, but it is of general agreement that the damper should start to lift at the point the hammer has traveled 1/2 of its distance. This is approximately the same as saying the damper lever should be contacted by the back of the key when the front of the key had traveled 1/2 of its distance. If possible, find one sample in each section that lifts correctly. If correct ones cannot be found, adjust the position of the damper lever at rest by changing the amount of damper wire that goes into the wire flange until the standard is met on one sample in each section. With the action out of the piano, block the lifting rail upward until it is touching the underside of the damper levers that we have just set correctly. With Yamaha pianos, this is easily accomplished by adjusting the pedal rod nut to make the rod longer. In the case of pianos without an adjustment on the pedal rod, a wedge may be inserted between the top of the key bed and the underside of the rail. But be careful that any system used is secure and will not move from that position during the process of adjustment. At this point, the lifting rail has been moved upward to a point where it is just touching a correctly adjusted damper. In this position, the lifting rail should be contacting all damper levers, and if not, the correction would be to loosen screws on any damper levers that either do not touch the rail or those that have been raised by the rail, lifting their dampers from the strings. Once the screw is loosened, the damper levers that did not touch will drop to the rail, and any dampers that had been lifted off the string will fall to the string. Now all the loosened screws can be retightened. It may be easier if all screws are loosened rather than trying to find the individual dampers to regulate. Of course, the decision will be made depending upon the number of problems. When retightening the screw, the damper will try to rotate. Problems caused by this rotation can be minimized by first tightening the screws by hand and immediately correct any rotation at that point by twisting the damper head to the correct position with your fingers. Next, the screws can be tightened a bit more, this time with the use of a screwdriver, but do not tighten them completely at this point. Again, straighten by hand any that are not aligned perfectly with the strings. Finally, tighten the screws with a screwdriver, this time tighten them all the way, but of course not too tight. Any dampers that rotate a bit from this final tightening can be aligned properly by the use of a pair of pliers on the wire just above the damper wire flange. A second pair of pliers on the wire flange will add a safety factor as you twist the wire to position. The only tools you will need include a small screwdriver to fit the screws on the damper wire flange and perhaps a couple of sets of pliers. This procedure is probably not as easy as it sounds, but on the other hand, it is not nearly as difficult as is generally perceived. Final checking for any dampers that move first can best be seen by moving the damper pedal a small amount and very quickly, sort of tapping the pedal. On the other hand, to observe the dampers that are a bit late, depressing the pedal very slowly will be more beneficial. Now we're at the point where we can check the work just finished by continuing with the second half of this section of damper adjustment, which is covered under Step 32. This step is a continuation of the last procedure. It is for evenness of pickup of dampers by the lifting rail and refining and improving the work done in Step 31. The purpose of having all the dampers move simultaneously with the lifting rail is not only for the beauty of sight, but the paramount reason is for evenness of damping. If the dampers do not lift together, they cannot come to rest on the strings simultaneously. And if they do not touch the strings together as they descend, it's impossible for the pianist to use partial pedaling, a very important technique that opens doors to total manipulation unavailable any other way. To test the condition in the piano, move the right pedal while observing evenness of pickup. If any unevenness is noticed, change the setting on the damper wire for that unit as you did in Step 31. Next, observe the damper heads as you depress the damper pedal slowly. If any damper heads rise with a twisting motion, it will be caused by the wedge dampers not being aligned with the strings. To correct this problem, hold the wire flange stationary with one set of pliers and using another set, rotate the wire to the correct position. Next, observe if any of the dampers rise with a tilting motion, where one end rises before the other. If the movement is very small, correction can be made by grasping the damper and with slight finger pressure, bend the wire to the correct position. For a larger amount, remove the damper from the piano and straighten it with the use of the jig as you did in the last step. Finally, check the damper spacing at rest. Damper spacing is controlled by the small portion of the damper wire that extends from the damper head, the first 2 millimeters or so, before it bends downward. To change the length of this neck portion of the damper wire, it's necessary to remove the damper unit from the piano and do the remedial work outside of the piano. First, place the pliers on the wire at the position of the last bend. This can be done by sliding the pliers down the wire until they stop. Straighten the bend out of the wire, which means the wire will now be pointing away from the damper block at approximately 80 degrees. Do not release the grip the pliers have on the wire yet. Now slowly release the pressure of the grip without releasing the grip itself. When the pressure is released sufficiently, slide the pliers to a new position on the wire, closer to the damper to make a shorter neck and further away from the damper for a longer neck. With the pliers in the new position, rebend the wire to the original configuration. This should complete the necessary bend to change the length of the neck on this damper wire. Damper wires are made of brass and usually can be bent 5 or 6 times before they will break. This means you should have some new damper wires available before very much bending is attempted. Replace the damper in the piano and set it at the correct position for damper lift. To visually check your work, move the pedal a very small amount and move it rapidly. And during the process of visual correction, don't forget the oral check to see that the damper does the job of stopping the sound. When the job is complete, it will satisfy both the sense of sight and the sense of hearing. You will need wire pliers, a screwdriver, and perhaps 2 sets of regular slip joint pliers. The dampers are now correctly adjusted, and we will move on to the pedals. One of the first things to remember about pedal regulation is that each pedal has 2 adjustments to consider. One for each pedal at rest, and this correction is made by changing the effective length of the pedal rod. The other adjustment is made when the pedal is depressed and is made at different points for each pedal. It can be at different places on different pianos. The regulation procedure under consideration at this step, damper pedal adjustment, is made with the right pedal at rest. Therefore, the adjustment is made by changing the length of the pedal rod. The correct amount of travel of the damper lifting rail before it touches the damper levers needs to be established. If there is no space, the dampers might not be resting on the strings and will not follow the string as it vibrates downward below its point of rest. The amount of lost motion should be about 1 millimeter of space between the top of the lifting rail and the bottom of the levers. With a bit of practice, you can train yourself to measure this space without removing the action by depressing the pedal a very small distance. To change the adjustment, change the length of the pedal rod by rotating the pedal rod nut to the proper position, then securely tightening the lock nut upward against it. On pianos that have a pedal rod of fixed length, change must be made in the thickness of the cushion the rod pushes against. Before going to the next step, make sure the adjustment did not result in poor dampening. This could be caused by setting the lifting rail too high. No tools are needed, but one word of caution is in order. By all means, check to see if the pedal lyre and the pedal lyre braces are securely attached to the underside of the piano before doing any pedal regulation. No matter how well the rest of the action is regulated, if the pedals are not correct, the pianist will feel uncomfortable and may complain about the performance of the entire action without realizing that the real problem is with the pedals only. As was mentioned in step 33, all pedals have 2 adjustments. This step covers adjustment of the distance the right pedal travels downward, or as the title states, the damper pedal's stop adjustment. During its travel downward, the pedal is lifting the dampers from the strings. The distance it travels after starting to lift the dampers will determine how far they are raised from the strings. The key raises the damper to a predetermined height, depending upon the distance the key moves after contact with the damper lever. This has been set by a prior step in this program. The step we are now considering should raise the damper to that same height, but by using the damper pedal instead. In that way, the damper will never drop onto the back of the depressed key and transmit a shock to the finger of the pianist as it might if the pedal raised the damper to a higher level than the key. The adjustment is found in different places on different pianos. Sometimes it is a block of felt between the underside of the key bed and the top of the pedal lever. On Yamaha pianos, the stop adjustment is a capstan screw located above the pedal lever and fastened into the underside of the key bed. This is a very good arrangement, for it allows for precise adjustment. On the pianos where the pedal lever comes to rest against the felt block, the adjustment is made by changing the thickness of the felt in the appropriate manner. To check, raise a damper by depressing and holding a key down. Focus your attention on the damper head and ascertain if it moves during the following test. Move the damper pedal up and down several times. The other dampers should rise to the same level as the one being held up by the key. However, the one being held by the key should not be moved in any manner by the pedal action. If the damper held by the key does move, it's an indication that the damper stop adjustment is set too high, allowing the dampers to be raised too far. Correction is made by turning the capstan in a manner to extend more of the capstan out of the key bed, which will shorten the movement of the damper pedal system. To check for a setting that is too low, reverse the procedure. Hold the pedal down and move the key up and down several times. All of the dampers will be raised by the pedal, and the one connected to the key you're moving should not rise to a higher level than it was raised by the pedal. If damper movement is noticed as the key is being pressed downward, it's an indication that the damper stop adjustment is set too low. Correction is made by turning the capstan screw further into the underside of the key bed, allowing for more movement of the damper pedal system. Some care and judgment must be used. If excessive force is used on either the pedal or the key, the dampers will rise above their normal position. The tools needed will depend upon the type of regulation required, but for Yamaha pianos, it will be a capstan wrench. When the pianist strikes a key forcefully, the back of the key hits the damper lever with such impact that the damper mechanism is moved upward very fast. It travels with such speed that it must be stopped, or it will continue to some point where it will make contact and damage something, or at least make noise. The mechanism for stopping this upward thrust of the damper system is the damper stop rail, a strip of wood fastened just above the top of the damper levers, the bottom of which is covered by a piece of soft felt. The purpose of the damper stop rail is to limit the free travel of the damper so the damper will not make noise as its travel is stopped, and also it will not travel very far away from the key. If the damper lever does leave the key and travel upward almost any distance, the momentum will return the damper lever to the key with such force that an annoying shock can be felt by the pianist. The position of the damper stop rail can be checked by depressing a black key firmly into the front rail punching and then lifting on the raised damper head. The damper should be free to move a small amount, about 1 millimeter, before the lever touches the stop rail, halting the upward travel of the damper. The damper stop rail must allow a bit of free movement of the damper lever beyond the position to which it is raised by the key. Otherwise, the touch characteristics will be affected in a negative manner, as the lever blocks against the hammer stop rail. In other words, the action of the key should not block the damper lever against the stop rail. The adjustment has to be made with the action out of the piano. The measurement for the amount of free play, if raised by the pedal, is greater than if raised by firm pressure on a black key, about 3 millimeters in this case. By loosening the screws that hold the rail in place, the rail can be raised or lowered as needed until the standard is met. For small movement, the use of pencil marks on the beam behind the stop rail may be of visual help. Return the action to the piano for the final check, which should be made with a black key, not the pedal. The only tool needed will be a screwdriver. Of the 37 steps, I suppose this one, covering the sostenuto mechanism, is thought to be the most difficult. But with proper understanding of sostenuto design, it is not difficult to adjust properly. The purpose of the sostenuto system is to create a situation that will allow the pianist to sustain individual tones without keeping the keys depressed. Success in regulating is assured if this point is kept in mind. If one damper can function properly with the sostenuto mechanism, and all of the parts are adjusted to form straight and parallel lines, then all of the dampers will function properly. Most piano makers use a type of sostenuto mechanism that is totally enclosed inside the action cavity, while some pianos use a design where part of the mechanism is attached to the action and therefore is separated from the rest of the mechanism whenever the action is removed from the piano. This explanation is for the type of mechanism found in most pianos. The standards are simple. The sostenuto blade should be positioned parallel to and just above the tabs. This position will allow for rotation of the blade without touching the tabs. When engaged, the blade should extend under each of the tabs 1.5 millimeters. Remembering the rule that all parts must form straight and parallel lines, Check to see if the tabs form a straight line that is parallel to the key bed. If not, there is error in the adjustments covered by steps 31 and 32. Also, looking downward through the strings, the tabs should form a straight line that is parallel with the front edge of the key bed. Bends in the damper wires can cause the tabs to be out of line. Another way to check for this alignment is to look at the damper wire flanges. They should also form a straight line. Next, check to see if the blade is parallel to the tabs. The blade is fastened to the bulkhead by brackets, and the brackets are adjustable up and down and can either be bent or spaced in or out in some manner. There's a series of tests to check the various adjustments that might be needed. First, remove the action from the piano and focus your attention on the blade and tab area inside the action cavity. As you move the sostenuto pedal, check to see if the blade and the tabs are parallel. If not, adjust the brackets up or down. Next, look at the same area and check to see if the blade touches the tabs. Remember that it needs to have minimum clearance, and usually a problem of touching at this point can be rectified by moving the bracket outward a bit, by bending it if the bracket is bendable, as in the case of Yamaha pianos, or spacing it outward with shims if the bracket cannot be bent. Next, engage all of the tabs by placing the blade under the tabs. Observe if the dampers have been raised to the same height as if raised by the right pedal. If not, an adjustment to the pedal stop mechanism is called for. It is located under the key bed above the sostenuto lever. In the case of Yamaha pianos, this stop mechanism is a capstan and can be regulated with a capstan wrench. If the piano does not have this type of adjustment, take appropriate action as indicated. Next, with the tabs engaged, confirm that the blade extends under the tabs 1.5 millimeters by checking along its entire length. If not, the blade should be moved to that position by either bending the bracket or spacing it with the punchings as required. Next, the pedal rod nut can be adjusted to place the blade in proper starting position. It should be pointing downward and out of the way of the ascending damper tabs in order for the adjustment to be correct. Secure the adjustment with a lock nut after the adjustment has been completed. To check whether or not the blade is being forced out of a straight line by the bracket, or to detect a blade that is bent, engage all of the tabs and release the sostenuto pedal very slowly. As dampers begin to drop, don't be concerned with individual dampers dropping out of sequence. However, large section movements out of sequence will indicate that the blade is not parallel with the tab line. For your final check, replace the action and test each key for proper catching on top of the blade. This is done by playing a key, pressing the pedal, releasing the key, and checking that the damper remains off of the string. Also test to make sure none of the tabs can pass by the blade. If they do, they will stay on top of the blade and disengage the damper from the string, allowing for an unplanned tone to continue to ring. This test is made by depressing and holding the sostenuto pedal down, then forcefully playing each of the keys. One additional bit of information. From this view, the tab should also form a perfectly straight line. If the damper lift by the rail is correct and some tabs are still out of line, it is because the tabs are not mounted exactly like their neighbors. Their lineup can be improved by either sanding or papering the damper wire flange at the point of contact with the tab. You will need a screwdriver and some means of bending the bracket should the need arise. The left or shift pedal is sometimes called the soft pedal. This name is not accurate. The way the pianist controls volume is by the speed with which the key is depressed. While shifting the action does cause some change in volume, the major change is to the tone character and color. The shift pedal accomplishes this difference without changing the touch of the keyboard. The amount of shift is at the discretion of the technician. Manufacturer specifications differ from one another. At one time in the early history of the piano, use of the pedal would shift the action far enough to allow each hammer to strike only one string, and may be the reason the pedal is also referred to as the una corda pedal. The amount of shift on a modern piano will generally be specified in one of two ways, each ending with a different amount of movement of the action. This movement is best observed in the A-graph section. One specification will have the hammer shift to a position where it will strike all three strings just to the left of the grooves in the hammer. The other specification is for the hammer to move about twice as far, to a position where only two of the three strings are struck, but this time, instead of being struck in the area of the hammer just to the left of the grooves, the center and right strings are struck by the left and center grooves of the hammer. To adjust this pedal, first remove any lost motion between the action shifting lever and the spot on the bottom of the keyframe where it makes contact by adjusting the nut on the top of the pedal rod. While no lost motion should be present, it is also very important that the pedal rod nut is not adjusted too high, or the action will be slightly shifted even at rest. Tighten the lock nut against the pedal rod nut as before. For the other adjustment, depress the pedal and observe the point of contact that stops the action shift. Usually it is a screw on the inside of the action cavity that's touched by the side of the keyframe. In the case of Yamaha, it is on the treble key block. Turn this screw to stop the movement of the keyframe at the required position to have the hammer strike the strings as desired. Final checking should be done with the key blocks inserted and secured in place. Make sure none of the hammers move so far as to strike the strings of two different pitches. Yamaha prefers the adjustment that moves the keyframe to the point the hammer will strike only two strings of each unison in the A-graph section. It doesn't limit the pianist, as the other specification does, for this approach allows the pianist to choose any gradation of tone color available by simply depressing the pedal to the desired location. The only tool needed is a screwdriver. This completes the 37 steps of grand regulation, one of the programs from Piano Technology as Seen by Yamaha, a master series. At this point, you can take a step back and enjoy your work. You have now regulated an action that will pass the scrutiny of the finest pianist. You should have an inner sense of satisfaction, knowing that with this type of regulation, you are directly contributing to the artist's ability to create music that will thrill the audience. We have now reached the place where a wrap-up is called for. I could reiterate the steps just covered. It is expected to summarize the subject at the end of any program. I could stress the importance of uniformity, of precision, of listening to the comments of the pianist, of aftertouch, or many other important items, but I choose not to. For these last few moments, I would like to call your attention to an area of importance that must be learned in order to become the best technician possible. But before I let you know this secret of success, I must set the stage so that I'm not misunderstood. In the next few moments, if I speak of speed, it is not the speed gained by cutting corners or saving time by not doing the best job you can. Just the opposite. It is the speed gained by organization, by dedication to purpose, by concentration, by striving to excel. If I speak of training, it is not the training gained by having an instructor force you to follow some routine until it becomes a habit. Just the opposite. It is a training only you can do for yourself, and far exceeds the goal that would be set by anyone else. It is the type of training that extreme interest and dedication mandates, and even forces you to take the one path above all others, that of striving to be the best, for no other reason than the satisfaction of being the best. I would call your attention to the subject of time. It's really all we have to offer, and what we do with the time we have, to a great measure, determines the type of technician we end up being. Every job has a time limit of some sort, and usually the most important jobs in our lives could use much more time than we have available to spend on them. Being the best technician is an extreme example of this problem. When was the last time the manager of an extremely important concert said to the piano technician, "This recital is so important that it's necessary to have everything exactly correct. Take all the time you need"? It would seem those words are not in their vocabulary. Instead, we have to do not only our best, but a perfect job, even when there is not enough time to do a perfect job. Here is where speed comes in. We can all do more than we think we can. We just need to stretch our limits and continually reach for goals a bit out of our grasp. We must, as individuals, find ways and techniques to develop all our skills to become progressively better and faster. It is amazing to witness a factory worker setting repetition spring tension with blinding speed and uncanny precision. We say, we could never do that, but I assure you, the factory worker is no more talented than you. Another point is how we use the limited time we have to work with. A fine technician knows that the time available to correctly and completely regulate only 1/2 of a hammer line is much better spent working on all the hammers, correcting the worst problems first, and making the entire group more uniform and closer to the ideal, even if perfection is not possible. But the best technician is expected to make the customer happy and to be able to solve all of the problems. To do this, either we must have unlimited time to work with, which is a rare situation, or dedicate ourselves to be able to solve any problem within the time available, regardless of the amount. Does that sound unfair and impossible? I can't answer the way you view this problem, but for us, remember, this is piano technology as seen by Yamaha, a master series.